talked about the N-channel NMOS enhancement load device. Okay, so this is this time we are talking of depletion load device. The difference is for a depletion NMOS device, well, you don't have to apply VGS. Okay, I mean VGS over here you can see since it is shorted, the gate terminal is shorted with the source terminal. VGS you can see over here is 0. Okay, you don't need VGS. This thick pink line over here is denoting that the channel exists even if you don't have any electric field being applied at the gate terminal. All right, so you have the channel. So due to this channel, there is always you can say a flow of current from drain to source. Okay, so I mean this current direction as given in the symbol reflects an NMOS device in which the channel consists of N-type particles, okay, or electrons. Okay, so this is drain, this is gate, and this is source. So unlike enhancement type load device, if you recall, the gate was shorted with the drain terminal. Okay, so here the gate is shorted out with the is connected with the source terminal. So VGS is 0. Okay, so actually we don't need VGS anyways. So what happens is that the only thing that matters over here that dictates how much current is flowing or which is responsible to turn off the transistor is VDD, is this supply. Okay, because you see over here VD over here VD, I mean VDS is also primarily it's VD. Okay, because VS is 0, your VS is 0, so you only have VD, and VD is what? It is equal to VDD. So if you recall that in a depletion mode device, NMOS device, unless you apply a negative VDD, so you create a space charge region which extends from drain to source, and somehow you reverse bias that channel, you turn off the device. Okay, so if you apply a negative VDD, you can turn off the device. You can have ID equal to 0, but so long VDD is there, it's a positive voltage. The field is as such that the flow of electrons continue from drain to source, okay, in this direction. So if you look at the curve, first of all you will observe that we have this current ID, and there are saturation and non-saturation regions. So pass beyond this point, your transistor, depletion type transistor, is in sat region. Okay, and over here for low values of VDS, which is equal to VD. Okay, and over in this configuration, this is primarily VDD, I must say. So this is non-sat, and you see in order to have the transition point to be a positive quantity, you recall that the threshold voltage is negative for depletion mode. Okay, so over here VGS is 0. Okay, VGS is 0, which can be seen over here. Okay, VGS is 0. So you're left with a negative of VTN. So VTN is the threshold voltage for the NMOS device, NMOS depletion type device. The difference between depletion type NMOS and the enhancement type NMOS is that for enhancement type NMOS, the threshold voltage is positive. For depletion type, it is negative. Okay, so this is less than 0. This implies that this quantity, negative of VTN, is greater than 0. It implies VDS at over here. This is positive. This all quantities are positive over here. So this is the positive quantities greater than 0. So the transition point is greater than 0, right? So for lower VDS or for small VDD values, you are biasing your transistor in non-sat. For higher values of VDD, you are moving your Q point you're biasing the transistor in the sat region for even for 0 electric field at VGS at the gate terminal. Okay. So the figure shows an N-channel depletion mode MOSFET, and can also be used as a load device, just like we had enhancement type N-channel MOSFET. We have a depletion mode, and that can be also used as a load device. It says so. It's a non-linear resistor basically. So consider the depletion mode MOSFET with the gate and source connected together. They are tied up together in figure 38A over here. This is 38A. So the current voltage characteristics are here, 38B. over here, and the transistor may be biased in either sat or non-sat regions, and the transition point is also shown on the plot. Now the threshold voltage of the n-channel depletion mode is negative, so VDS sat is always positive. So this is a negative quantity. So you see why it's negative. If you recall what we have discussed in the few lectures before, um, even if you don't have an electric field, the fabrication of the depletion type NMOS is as such. So this is not enhancement, this is depletion type, and this is the transistor. This is the this is the fabrication cross-section view of the how the transistor depletion type MOSFET is fabricated. So you have depletion type NMOS device over here. Why it's NMOS? Because the particles that are responsible for conduction of current from source to drain in conventional manner are electrons. Okay, these are negatively charged particles. Okay, so this is depletion type NMOS. So the fabrication is as such that even with no electric field, the channel is there. The channel is there. So you have the a non-zero ID already established because of the channel. So if, for example, over here, you see what happens is if you apply a positive electric field, I mean, you connect a battery like this, okay, positive, and then you have negative over here, and you connect it to the source terminal. Okay, which is connected to the bulb or the substrate. So this negative, owing to this negative over here, the p-type, I mean the holes are going to be they get attracted to the base of these they start accumulating over here at the bottom of the substrate. Okay, and what are left behind is a negatively charged minority carriers over here in the channel region, which is already n-type. So that somehow enhances, or that you can say forward biases the junction, the channel junction with the substrate, which is reverse biased. So this VGS greater than 0 causes electron accumulation layer over here. Okay, so this somehow what it does is it does increases the width of the channel. Okay, so the current from drain to source increases. The current from drain to source increases because the channel width increases, so that you have more space charge density over here. So the current is going to increase. So the current is going to increase over here. For the other case, if VGS is less than 0, I mean the battery is connected as such, so you have negative charge on the gate. You must say the gate metal. Okay, so the positive is connected with the source. Okay, so something like this. This is connected, so it's positive over here. It's negative. So you have negative charge over here, and this positive, somehow it is repelling. So I mean, these holes are being repelled over here by the positive charge of the battery terminal, and they are going to reverse bias this PN junction. So this is a PN junction over here, which is reverse biased. So this junction, owing to the reverse biasing of the junction, you see there is a depletion region that gets introduced to in the channel, and somehow it reduces the width of the channel. The channel width reduces, so it chokes the channel. So as you see, the threshold voltage has to be negative, because applying a negative voltage, applying VDN, which is like threshold voltage for depletion type NMOS. This is NMOS, so this is N over here. Less than 0, somehow causes the ID current to reduce. Okay, so this in fact reduces with increasing negative voltage applied at the gate terminal. Okay, and then it chokes the channel. So choking the channel results in zero ID. Okay, so if over here you see the only thing you need to turn off the transistor is VDD. Okay, if you apply a negative VDD, if VDD is less than 0, then in that case your ID starts decreasing, and point comes that ID goes to 0. ID goes to 0. So the transistor is turned off. So the transistor is turned off. So if you apply a negative VDD, the transistor is off. If you have a positive VDD, well, it's going to enhance the current ID. Okay, so that's the idea behind the depletion mode. But you don't need VGS. VGS is zero. VGS is zero even for the zero VGS, since the channel is already there in the fabricated device. So the current is, you have a non-zero current even without electric field at the gate. So that's the theory behind the depletion mode MOSFET. We have talked about this in detail before. If you have not checked the video, please go ahead and look at the depletion mode construction of MOSFETs. Okay, um, so the idea is to use this as a nonlinear device, as a nonlinear resistor. So this is again your, let's call this a nonlinear resistor R, and to use this nonlinear resistor R to build up a digital inverter circuit. So what we are here after is a depletion load device is going to be used in conjunction with another MOSFET. And you see another MOSFET, call it a driver MOSFET, is not necessarily a depletion mode. It could be an enhancement mode. So for example, over here, this D is the driver mode transfer. MD is your driver transistor. This is your load transistor, which is simulating or emulating a non-linear resistor. I mean, this is the load. So this, you can say that this emulates itself, it appears itself to be a non-linear RD resistance, just like in enhancement mode NMOS device. This is depletion mode NMOS device, but this is being used in conjunction with the together with enhancement mode. This is not depletion mode, this is enhancement mode. So you need the input voltage, okay, and this input voltage, which is equal to VGSD over here, right? Because the source is at 0, you see Vs is at 0. In conjunction with the input voltage is going to define what the output voltage is. So the thing is, the driver transistor can either be driven in saturation or non-saturation. Okay, so but anyways, you need to apply the electric field. This is enhancement. Okay, over here you don't need VGS. Okay, you can see that the gate and the source are shorted out. Okay, so the difference between VGS, you can write this as VG minus Vs is 0. It's at the same potential that can be seen. So the potential difference is 0. VGS is 0. You don't need VGS. So without any VGS, there is the drain to source current in the load transistor. Okay. So with the depletion type MOSFET, we are using another MOSFET, which is enhancement type, and both driver and load are NMOS devices. Okay. So as shown in figure 39, this is figure 39 over here. So we are going to use this circuit. They're going to use this nonlinear RD resistor with NMOS enhancement device, which can be used as an amplifier or as an inverter in digital logic circuit. Okay. So both the load and the driver transistors, they can be biased in the saturation or in non-saturation region depending on the value of the input voltage. Okay. So the idea is very similar. I mean, previously in the DC analysis of the last video, we talked about the enhancement mode NMOS device, which was being used as a nonlinear resistor. Okay, so once you have a high value of Vi, if Vi is large, it creates a large current. Okay, so IDD and IDL are basically the same series currents, and due to that, you remember that IDRD drops increases. Okay, as Vi increases, IDRD drop increases. As a result, the output voltage decreases. Okay, so it's like an inverter circuit. On the other hand, if your Vi is just decreasing, then your Vout is increasing. So it's an inverter circuit, because if you decrease Vi, you tend to decrease the space charge density in the enhanced channel or the inversion layer. Okay, so the current reduces, the drop reduces, and the V0 increases. Okay, so the V0 increases in that. So it's an inverter circuit. Increasing Vi decreases V0, decreasing Vi increasing V0. Okay, so it's the same idea that we have discussed in the previous lectures. So let's use this as an inverter circuit, and let's try to analyze this example of your text 3.10. What it says is the objective is to determine the DC transistor currents and voltages in the circuit containing a depletion load device. So we have the depletion load device over here. That is the load device, and then we have the driver device, MD2 transistors. Again, we don't use surface mounted devices or thin film resistors or in digital circuits. The MOSFET itself is emulating a load over here. It's simulating a load over here. So consider this circuit in figure 39, which you have seen before. Let VDD be 5 volts, so their values. So VDD is now 5 volts, and you're given with the conduction parameters of your load MOSFETs and the driver MOSFETs, respectively. And you're also given the threshold voltages, and you recall that for the load device it's a depletion type, so VTN it has to be less than 0. So you can see over here there's a negative sign, it's minus 2 volts. Then you have enhancement mode device, which is a driver transistor, so VTND is positive, so this quantity is positive. Okay, so you are required to determine the output voltage for VI equal to 5 volts. Okay, so the input is 5 volts. So let me write this down as so VI is basically your VGSD. Okay, that means the electric field that you're applying at the gate terminal of the enhancement driver MOSFET is 5 volts. Okay, and this is going to create a channel. This is going to create a channel due to which there's a current that is going to flow IDT, and this current will be the same as, so the drain currents in the two transistors are in series, so they are equal. Okay, so we have IDT equal to IDL. And my guess is, so we have to start with an assumption as we've done earlier. Now, if this VGSD 5 volts, which is much greater than the threshold voltage, I mean the difference between VGSD, you see over here, VGSD, the overdrive voltage, VGSD minus VTN, the minimum that was required to turn on the lower MOSFET was 1 volts. Okay, so minus VTN D is 4 volts. The difference 5 minus 1 is 4. So you see, the thing is, the input voltage is high, much higher than the than what is required. So if it is high, then my guess is that the output will be small. Okay, because this is an inverter circuit. That's what an inverter circuit is supposed to do. So when the output voltage is small, that means your VDSD, which in this case is equal to V naught, is small. Okay, VDSD is small. That means in the curve of IV characteristic of a transistor, you are somewhere down VDS sat. Okay, so at this point is defining your transition point. So this is your VDS sat, VDS sat, VDS sat. So that transition point is somewhere on the VDS axis. So this is your VDS axis, and this is for the load transistor. Okay, so if your output voltage is small, then you should be somewhere here. This is small. For large VDS, you bias your transistor in the saturation region. So this is an assumption. Okay, so as it says, let's assume that the driver transistor MD, this driver transistor MD, the load transistor, is biased in the non-sat region, and the load transistor is biased in the saturation region. Okay, let's continue with this assumption. If this assumption is correct, then it holds that these two currents are equal, and the driver MOSFET, enhancement type NMOS, which is this current voltage relationship is for non-sat driver MOSFET. Okay, so this is non-sat driver MOSFET IV relationship, because in saturation, once you have the transistor in saturation, you know that the current is not dependent on this is the current axis, and the current is not dependent on a VDS no more. Okay, even if you go on increasing VDS, I doesn't increase. So this region is sat region. Okay, so since VGSD is VI, okay, we are just equating these currents to be equal. So this is non-sat IV characteristic. This is sat region voltage and current relationship, and you see over here this gate is shorted to S. Okay, so VGSL is 0. All right, so this thing you don't need to bother about this VGSL, it's 0. VTN for depletion type is negative, so this becomes a positive quantity. This is 0 over here, VGSL, and then you just substitute -2. KNL, the conduction parameter for the load MOSFET, is 10. So you see this is 10 over here. Okay, so this is coming over here. And then for the driver transistor, which is um, which is in the non-sat region, we have VGSD equal to VI. Okay, you see over here, VI is VGSD, and the VDSD is V naught over here. You see V naught, because the source is at 0, so uh, V naught is in fact equal to VDS or VD. So just let's substitute those values. You see over here for VDSD, these values they become equal to V naught. Okay, this is V naught, this is V naught, and this equation is going to give you basically a quadratic. So VGST is VI, and VI is 5 volts. You know, 5. This is 5. VTND is given. That's 1 volt. That is also known. So the only thing that is unknown is V naught. Okay, the conduction parameters are given for the driver and MOSFETs. This is 50 microamps per volt square. So substituting this, you get yourself a quadratic, and solving this quadratic, this is the quadratic. I should rearrange the terms. So solving this quadratic gives you two values of V naught. The output voltage could be 7.9 volts or 0.1 volts. And a clever guess is just looking at those values. I mean, you have the battery that is driving the load transistor, and the driver transistor is 5 volts. So you cannot have, I mean, the transistor cannot go on creating more energy. I mean, you cannot have output voltage greater than VDD. So the only correct option that a viable option that looks like is V naught is 0.1 volts. Okay, and to check its validity, okay, I mean this was the first hunch. So since the output voltage cannot be greater than VDD, the valid solution is 0.1 volts. So the current is, you may write it as well, since the current is series, either you use this expression or use this expression, the same thing. So you see this becomes 4, this becomes 40 microamps. 40 microamps. So this is what it is. So this is the current, just because we are supposed to find the current and the output voltage. That in this case, this is VDSD. Okay, so we have VDSD, we have ID. So these two parameters were supposed to be found out. Now, just to see the validity of this equation, the other way around is, you see, since VDSD is V naught over here, VDSD is V naught, and this is less than, this is 0.1, is less than the overdrive voltage VGST minus VTND, which is 4 volts, right? I mean, this defines your VDSD sat, isn't that right? So VDSD for the lower transistor, VDSD sat is 4 volts, and 0.1 is much less than the 4 volts. Okay, so if in the curve this transition point is occurring at 4 volts, this transition point is at 4 volts, you're somewhere here at 0.1 volts. So like I said before, for the inverter, if 5 volts is a large voltage compared to 1 volt, so the output voltage is small, that defines that VDSD is small. So you're somewhere down the curve over here. That means you're in the non-sat region. This is your non-sat region, right? This is your non-sat region. Non-sat region. So your this is for the driver transistor. Driver transistor is therefore biased in the non-sat region. This is the assumption that we took before, as assumed. Similarly, if you check for the load transistor, VDSL, which is nothing but VDD minus V naught. So let's see, VDD minus V naught is 4.9 volts. This is much greater than VGSL minus VDNL. So VGS is 0 for the depletion type, and VDN is the negative quantity, which becomes positive. Negative 2 is 2 volts. So 4.9 is greater than 2 volts. That means for the upper transistor, the transition was occurring at 2 volts. Okay, so you are somewhere at here 4.9 volts. So you are in sat region. Okay, so if you are here, your VDS is, which is equal to V naught. So this is not V naught. This is VDSL. So VDSL is basically greater than the transition point, greater than the saturation point. So that's why your upper transistor is in saturation, and the lower transistor is biased in non-sat. So upper transistor is biased in saturation. So that's what we assumed before, and that's how we proceeded. I mean, the lower transistor was in non-sat, upper transistor was in sat, and this analysis, the current and the voltages that we got. I mean, the output voltage V naught, okay, 0.1 volts, This is 0.1 volts, and the current that we obtained are correct, indeed correct, based on these assumptions, because for the lower transistor we are lower than 4 volts, so we are in non-sat, and for the upper transistor, the load transistor, the transition point was 2 volts, and we are above that point, so we are in the saturation region. So the load transistor is in saturation, and the non and the driver transistor is in the non-sat region. Okay, so that's the idea. Now, the voltage transfer characteristic for the NMOS inverter circuit with depletion load in figure 39 is obtained from piecewise analysis, as we've discussed before, for an enhancement type MOSFET inverter. Here we have one depletion type and the other was enhancement. So these results are shown in figure 40. This is figure 40. Okay, so the voltage transfer characteristic of NMOS is very similar to that of enhancement type. What happens as you go increasing Vi, your output is decreasing. Okay, so your output decreases over here. I mean, this for large values of Vi, you're somewhere over here. Okay, but for small values of Vi, for example, over here, if your transistor is off, 5 volt is your VDD. Okay, so for no current, you are having, and for a very small, even for a very small voltage, input voltage. For small input voltage, you have a large output voltage. For large input voltage, you have a small output voltage. This is again V naught. So this is transfer characteristics for inverter circuit. So you see over here for an input voltage, for example, less than 1 volts. What is 1 volts? 1 volts is your threshold voltage. For what? For VT and D. Okay, because VTNL is -2. Okay, if you must recall these values. VT and D is 1 volts. Okay, and your VT and D is -2 volt. VT and L, because that's depletion type. So let's put down these values over here. So VT and L, the load is -2 because it's depletion type, so it's negative. Okay. So if your input voltage is less than 1 volts, you see over here in the circuit, the input voltage is less than the threshold voltage. Basically, your transistor is off. There is no current. Then there is no current. Then I mean, there is no drop across. There is no drop across VDSL. So VDD is your output. Okay, VDD is your output. So for input voltage less than 1 volt, the driver is in cutoff. The driver MOSFET is in cutoff, and the output voltage is 5 volts. Okay. So what happens is that when the input voltage is just greater than 1 volt or around 1 volt, the driver transistor is biased in the saturation region, and the load device is in the non-sat region. Okay. So for the driver transistor, so what it means is that around 1 volts, because 1 volt is a small voltage, 1 volt over here is a small input voltage which is around threshold. For small input voltage, you're going to have, because the current is small, okay, so the drop is small across VDSL, so you're going to have a large V naught. So what does it mean? A large V naught means VDSD is large. VDSD is large means you are in the saturation region. So you drive the transistor, the bottom transistor in saturation region. So when so that means the driver transistor is biased in the saturation region. So that's what it is. And the load device goes in the non-sat region. Okay. Why it goes in the non-sat region is that because for small input, your output is large. So the difference over here, VDSL, this quantity becomes small. So this is going to drive this transistor into the non-sat region. So then this goes into the non-sat region. This load transistor goes in non-sat, and this transistor goes in saturation region. And this is happening when, so these two things are happening when your Vi is a little greater than 1 volts, okay, or around 1 volts, you must say. But when the input voltage is approximately 1.9 volts, then both transistors are biased in saturation region. Well, if you're going to increase Vi, you're going to affect your V naught, which is going to affect VDSD. So if the input voltage increases, if the input voltage over here increases, then this decreases. Okay, the VDSD decreases. So VDS decreases, V0 decreases, so it is affecting the saturation or the non-saturation. So it's going to drive the load transistor also in the saturation part. It's also going to drive this in the saturation region as well. So both the transistors in the saturation region. But as the input voltage becomes much larger than 1.9 volts over here, if you are going to close to be equal to 5 volts, then as you've seen in the example, uh, the driver is biased in non-sat, and the load is in the saturation region. So that is like basically what is shown in the example. I mean, close to 5 volts when this is for Vi. Okay, over here Vi equal to 5 volts. Your driver transistor is a non-sat, and your load transistor is in saturation region. So then it's the other way around. So you see which transistor is in sat and which transistor is non-sat, or both are in sat. It all depends on the input voltage. Okay, and you have to see uh, how you are affecting from the input voltage VDSD, which is the output voltage, and this in turn gives you the idea, and you have to also see what is VDSL. So these two parameters will give you the idea where the transistor is going to be biased in SAT or non-SAT. Okay.